All right, welcome everyone. I am so pumped to have you here today. What we're doing in this explainer is going on a bit of a journey. We're going to step into the shoes of network architects and literally engineer the ultimate digital logistics machine from the ground up. If you've ever found yourself wondering how the internet actually holds itself together, well, you are definitely in the right place. Let's get into it.
Okay, just a quick look at our engineering blueprint for today. We'll start with the unreliable internet problem, build our digital shipping ledger, look at fail-safes and timers, figure out how to break the speed limit, and finally, admire our modern reliability engine.
So, part 1, the unreliable internet problem. We've got to face a pretty harsh reality right out of the gate here. Raw internet data transmission, it is inherently beautifully chaotic. Seriously, I want you to think about this for a second. How is it that your 4K streaming never seems to glitch, your downloads are perfect byte for byte, and your messages always arrive in the exact right order? How does that actually happen when, out in the digital wild, packets of data are just constantly getting dropped, delayed, or totally scrambled? Honestly, if the physical postal service lost packages as often as a raw network does, we'd all be rioting.
Because in a raw, stateless network, it is literally the Wild West. Packets are dropped, they show up out of order, or they just vanish entirely, heading to some unknown destination. But by using TCP order, we're taking all that raw chaos and we're forcing it into a structured, perfect, highly reliable digital logistics pipeline.
Moving right along to part 2, the digital shipping ledger.
So, to actually tame all that chaos we just talked about, we need a foundational base model for our engine, right? A way to track our data, exactly like we track physical packages moving through a massive warehouse. And this digital shipping ledger operates on what we call a dual contract. On one side, we have the sequence number. Now, this doesn't just count packets. It pinpoints the exact, precise bytes being sent in the overall file. And on the other side is the acknowledgement number, or the ACK. This basically acts as our return receipt. It explicitly tells the sender, hey, I got this, and here's the exact next byte I'm expecting from you.
Now, this dual contract builds what's essentially a continuous mathematical engine. It's wonderfully simple, but honestly incredibly robust. Step 1, you take the current sequence number. Step 2, add the exact number of data bytes you just transmitted. Step 3, that combined total becomes your next expected sequence, or your ACK number. Just like that, it creates this unbroken chain of accountability for every single byte of data.
Over 4,294 million and change. Now, why does this matter? Well, this massive number is the physical limit where sequence numbers actually max out and wrap around to reset to 0. You might be wondering, wait, on a super high-speed network, wouldn't overlapping sequence numbers cause total chaos? And yeah, they absolutely would if the internet didn't have a built-in Grim Reaper. Thanks to maximum time to live limits that are enforced by routers, usually defaulting to around 255 seconds, any of those old delayed packets effectively just die and are discarded long before our fresh cycle of sequence numbers can ever catch up to them. Pretty cool, right?
And, to squeeze out maximum performance without totally wasting bandwidth, we use this brilliant little concept called piggybacking. So instead of wasting valuable network space by sending blank, empty receipts back and forth, our engine seamlessly weaves the data flow and the confirmation flow together. Every packet does double duty. It carries new payload data to its destination, and simultaneously, it carries the receipt for the data it just got from the other side.
All right, part 3, fail-safes and timers.
Since we know packet loss is just an inevitable fact of life in the real world, we have to install a reliable heartbeat into our engine. And this is basically a highly precise timer. The absolute second we send a packet, this timer starts ticking down. If that timer hits 0 before we get our return receipt, our engine automatically assumes the worst-case scenario that the data was just lost in the void, and it instantly triggers a retransmission. It is our ultimate fault-tolerant safety net.
Which brings us to part 4, breaking the speed limit. Okay, so at this point, our engine is super safe, but man, is it painfully, agonizingly slow. We desperately need to install some turbochargers here. The big bottleneck, it's called stop and wait. See, if we force our engine to wait for a perfect confirmation receipt for packet number 1 before it's allowed to send packet number 2, we are totally starving our network. We are completely wasting our bandwidth. On a modern high-speed connection, the physical time it takes for those signals to bounce back and forth becomes a massive, massive penalty. If you look at this breakdown, it's pretty stark. We absolutely have to upgrade and move away from that sparse, staircase-like trickle of stop and wait that was built for early, slow networks. The modern upgrade? Buffered pipelining.
We want a dense, parallel laser line of data that gives us extremely high bandwidth utilization, custom built for modern high-speed infrastructure.
So, how do we actually do it? Well, here is our ultimate speed upgrade, the sliding window breakthrough. By using internal memory buffers to hold pending data, we can now process and send multiple packets out onto the network in parallel. We aren't just sitting around waiting for individual receipts anymore. The window slides forward only as cumulative confirmations come in, which totally liberates our network's true speed capabilities while keeping everything perfectly safe.
Now, to make this brand new high-speed highway even smoother, we use a really clever 1-2 punch for optimization. Part 1 of the combo is the cumulative ACK. Because our buffers are processing data so incredibly fast now, the receiver doesn't actually need to send a receipt for packet 1, then packet 2, then packet 3. It can just send a single, comprehensive message saying, hey, I have perfectly received everything up to packet 4. This drastically reduces our communication overhead and saves all that precious bandwidth for the actual payload data we care about.
And finishing up the combo is part 2, selective acknowledgement, or SAC. If we're blasting out dozens of packets at once and just one single packet gets lost in the middle, a standard cumulative receipt would force us to resend everything from that point onward. But SAC acts a bit like a packet X-ray. It explicitly tells the sender the precise left and right boundaries of the fragments it did receive. And this lets our engine perform a completely surgical recovery, just plugging the exact missing holes without blindly resending data we already successfully delivered.
Finally, part 5, the modern reliability engine. Okay, let's take a step back for a second and just admire the completed TCP architecture we've built here. Honestly, it feels like magic, but it isn't. It is just the perfect orchestration of these 4 logical pillars. We've got our sequence tracking keeping perfect order, our fault tolerance timers ensuring nothing is ever truly lost, our buffers and sliding windows giving us incredible parallel efficiency, and our surgical SAC recovery quickly patching any bumps in the road. Together, they take the completely unpredictable, chaotic reality of physical networking and transform it into a flawless, invisible digital pipeline.
It really makes you think, doesn't it? As you sit there right now, device in hand, flawlessly streaming my voice without a single dropped byte, what other invisible miracles are happening inside your device, operating flawlessly in the background of your digital life right now? It's pretty mind-blowing. Anyway, thank you so much for exploring this with me today, and keep asking those questions.